Hello everyone, and welcome back to K-Tips. In today's video, we're going to explore the structure of Dockerfiles, a key component for building Docker images. Understanding how Dockerfiles work can greatly improve your ability to create, deploy, and manage containerized applications. Whether you're just starting with Docker or you're an experienced developer looking to refine your skills, this video has you covered. We'll walk through each instruction step by step, covering everything from selecting a base image to optimizing your final build. And here's the exciting part, stick around until the very end, because we'll share advanced tips and techniques to elevate your Dockerfile expertise. You definitely don't want to miss it. From Python 3.9 Slim. To get started, let's look at the first line of our Dockerfile, from Python 3.9 Slim. This line is crucial as it sets the foundation for our Docker container. The from instruction specifies the base image for all the subsequent instructions in our Dockerfile. Think of it as laying the groundwork for our container. Every Dockerfile must begin with a from instruction, as it tells Docker which base image to use. Here, we are using the official Python image available on Docker Hub. The term Python refers to the image repository, which is maintained by the Python community and Docker. Using an official image ensures reliability and regular updates. The 3.9 tag specifies that we want to use Python version 3.9. This is important because it provides consistency. By specifying a version, we make sure our application runs in a predictable environment, avoiding potential issues that could arise from version discrepancies. The term Slim indicates that we are using a lightweight version of the Python 3.9 image. This variant includes only the minimal packages needed to run Python, excluding unnecessary components. Why is this beneficial? Because it results in a smaller image size, which means faster downloads, reduced storage usage, and quicker deployments. By using from Python 3.9 Slim, we are building our container on a solid, efficient, and reliable foundation. This Slim variant ensures we have a streamlined environment that includes just what we need to run Python, keeping our container clean and efficient. In summary, this line sets the stage for everything that follows in our Dockerfile, ensuring we start with the right tools and a consistent environment. Let's talk about environment variables in Dockerfiles. ENV instruction. The ENV instruction is used to set environment variables within a Docker container. Environment variables are key value pairs that can configure the behavior of the software running inside the container. By using environment variables, you can make your containers more flexible and easier to manage. The ENV instruction allows you to set environment variables that will be available to the container and its applications at runtime. These variables can be used to configure various aspects of the application, such as file paths, application settings, and resource limits. The syntax for the ENV instruction is straightforward: env key equals value. Sensitive information, such as API keys or database credentials, can be set using environment variables, keeping them out of your source code and reducing the risk of exposure. env Python don't write bytecode equals 1. This setting tells Python not to write .pyc files. By default, Python compiles your scripts into bytecode files with a .pyc extension and saves them to disk. In a Docker container, especially during development, code changes frequently. Writing .pyc files can lead to unnecessary disk usage and clutter the container's file system. By setting Python don't write bytecode equals 1, we prevent Python from generating these files, keeping our container lightweight and clean. env Python unbuffered equals 1. This setting ensures that Python output is written directly to the terminal without buffering. Typically, Python uses buffered I/O, which means it collects output in chunks before writing it out. Buffered output can delay the visibility of logs, which isn't ideal for real-time monitoring and debugging, especially in a containerized environment where immediate feedback is crucial. By setting Python unbuffered equals 1, we disable this buffering, ensuring that our logs are immediately available and more responsive. This is essential for monitoring and debugging applications running inside containers. In summary, the ENV instruction is a powerful tool for setting environment variables that configure the behavior of your applications inside Docker containers. It enhances flexibility, portability, and security by allowing you to manage configuration settings centrally and dynamically. With practical examples like Python don't write bytecode and Python unbuffered, we can see how environment variables help tailor the application environment to be more efficient and responsive. ARG Instruction. Let's discuss the ARG instruction in Dockerfiles with the example ARG environment equals development. The ARG instruction defines build time variables that can be passed to the Dockerfile during the build process. These variables allow you to customize and control the build without hard-coding specific values. In our example, ARG environment equals development specifies a variable called environment and assigns it a default value of development. This means that unless otherwise specified, the environment variable will be set to development when the Docker image is built. This setting provides flexibility by allowing you to customize the build process based on the environment. For instance, you might want different dependencies or configuration settings for development, staging, and production environments. You can pass a different value to the environment variable when building the Docker image using the build.arg flag. For example, if you want to build the image for a production environment, you can run docker build.arg environment equals production t-myapp. This command sets the environment variable to production during the build process. Using build time arguments simplifies the process of switching between environments and ensures build-specific configurations do not leak into the runtime environment. ARG variables are only available during the build process and do not persist in the final image. Here's an example to illustrate how ARG can be used in a Dockerfile. Run if $environment equals development, then pip install our requirements dev.txt. Else pip install our requirements.txt. Phi. In this example, the run instruction checks the value of the environment variable and installs the appropriate dependencies based on whether it is set to development or production. The ARG environment equals development instruction introduces build time flexibility, allowing you to customize the build process for different environments, making your container setup more adaptable and efficient. Let's talk about the run instruction in Dockerfiles. The run instruction is used to execute commands in a new layer on top of the current image and commit the results. This instruction is one of the most powerful and flexible Dockerfile instructions, as it allows you to install packages, run scripts, or perform any command line task needed to set up your environment. Here's a simple example to illustrate the use of the run instruction. Run apt-get update and apt-get install y-curl. In this example, the run instruction updates the package list and installs the curl utility. The and operator chains the commands together, ensuring they run in sequence. When using the run instruction, it's important to combine multiple commands into a single instruction to reduce the number of layers and minimize the size of your final image. The run instruction allows you to execute commands, install dependencies, and configure your environment. By understanding how to use run effectively, you can create optimized and reliable Docker images that are ready to run your applications. For instance, you can use it to install dependencies for your application, compile code, or download additional resources. Let's move on to the next important instruction in our Dockerfile, WORKDIR/app. The WORKDIR instruction sets the working directory for any subsequent instructions in the Dockerfile. Think of it as setting the current directory in a shell environment. Using WORKDIR helps in organizing the file structure inside the container. By setting a specific working directory, we ensure that all our application files and dependencies are stored in a designated location, making the container's file system more organized and easier to navigate. It also makes your Dockerfile more consistent and less error-prone. Instead of specifying absolute paths in every instruction, you can use relative paths, which makes the Dockerfile cleaner and easier to maintain. If the specified directory doesn't exist, Docker will automatically create it for you. This means you don't need an extra step to create the directory, simplifying your Dockerfile. Additionally, WORKDIR improves layer caching. Docker uses layer caching to optimize builds, and by using WORKDIR, we can provide clear separation between layers, improving the reuse of previously built layers. For example, WORKDIR/app copy requirements.txt. Run pip install our requirements.txt. Copy ... By copying and installing dependencies separately, you avoid rerunning pip install every time you change non-related code files, making your builds faster. In summary, the WORKDIR/app instruction sets the stage for all subsequent file operations and commands, ensuring they are executed in a consistent and organized manner within the /app directory. This helps keep our container environment clean, efficient, and easy to manage. Copy instruction. The copy instruction is used to copy files or directories from your host machine into the Docker container. This ensures that all the necessary files and dependencies are available within the container for your application to run. For example, consider the following instructions. First, we have copy requirements.txt/app/. This line copies the requirements.txt file from your host machine into the /app directory inside the container. The requirements.txt file typically contains a list of all the Python dependencies that your application needs. Following that, we have run pip install our requirements.txt. This run instruction tells pip to install all the dependencies listed in the requirements.txt file that we copied earlier. The R flag stands for requirements and instructs pip to read the list of packages from the specified file and install them. Next, we have the instruction copy./app/. This line copies the contents of your current directory on your host machine into the /app directory inside the Docker container. The dot represents the current directory where your Dockerfile resides, and /app/ is the target directory within the container. Why this order matters? The reason for copying requirements.txt first and installing dependencies before copying the rest of the application is layer optimization. Docker caches each layer during the build process. By separating the dependencies installation step from copying the rest of your application, you avoid reinstalling dependencies every time you change your application code. For example, Docker only reruns pip install if requirements.txt changes. If your application files, e.g., source code, change but requirements.txt does not, the dependencies are reused from the previous build, saving time. Copying the entire working directory ensures all the application code, configuration files, and other assets are included in the container. In summary, first copy requirements.txt and install dependencies, then copy the rest of your application. By organizing your copy and run instructions in this manner, you create an optimized, logical flow that minimizes build time while ensuring a seamless and reliable containerized environment for your application. Let's talk about the expose instruction. The expose instruction is used to inform Docker that the container listens on the specified network port at runtime. In our case, we use expose 8000 to indicate that our application inside the Docker container will be accessible through port 8000. This is important because it tells Docker which port our application will use to communicate with the outside world. By specifying expose 8000, we make it clear which ports need to be open for the application to function correctly. This improves the readability and documentation of your Dockerfile, making it easier for other developers or DevOps engineers to understand and manage the container. It's worth mentioning that while the expose instruction itself does not publish the port to the host machine, it serves as a best practice to specify the exposed ports in the Dockerfile. This ensures that anyone running the container knows exactly which ports need to be mapped. In summary, the expose 8000 instruction tells Docker that our application will listen on port 8000, preparing our container to handle network traffic on this port. This ensures our application is accessible and clearly documents its network requirements. Now, let's discuss the CMD instruction in our Dockerfile. The CMD, Python, app.py, line specifies the command to run when the container starts. Unlike the run instruction, which executes commands during the build process, the CMD instruction sets the command that will be executed when a container created from the image is started. The primary purpose of the CMD instruction is to define the default executable for the container. In this example, it instructs the container to run the Python interpreter and execute the app.py script. This means that when you start a container using this Docker image, it will automatically run the application defined in app.py. There are two forms to specify the command. Exec form, the preferred method, which provides the command and its arguments as a JSON array. For example, cmd, python, app.py. This form ensures that the command is executed directly without involving a shell, making it more secure and efficient. Shell form, the command is provided as a string. For example, cmd python app.py. This form involves a shell, which can be useful if you need shell features like variable substitution, but it's generally less secure. The CMD instruction can be overridden at runtime. When you start the container, you can provide a different command if needed. For example, running docker run image_name command will execute the specified command instead of the one defined in CMD. By defining the run command with CMD, you ensure that your application starts automatically when the container is launched, streamlining the deployment process and making it easy to manage and deploy your applications in a consistent environment. Next, let's explore the ENTRYPOINT instruction. The ENTRYPOINT, Python, app.py, specifies the command that will always be executed when the container starts. Unlike the CMD instruction, which can be overridden by supplying a different command at runtime, ENTRYPOINT is more rigid and ensures that the specified command is always executed. In this example, ENTRYPOINT, Python, app.py, tells Docker to always run the Python interpreter and execute the app.py script whenever a container created from this image starts. This ensures consistent application startup. ENTRYPOINT allows us to define the main command that should run our application, making the behavior of our containers predictable and reliable. It uses the exec form, where the command and its arguments are provided as a JSON array. This ensures direct execution without involving a shell, making it more secure and efficient. A key advantage of using ENTRYPOINT is its ability to work in conjunction with CMD. When both are specified, the command in CMD provides default arguments passed to the command specified by ENTRYPOINT, allowing flexible yet consistent entry points for our application. In summary, ENTRYPOINT, Python, app.py, ensures that our Python application always executes when the container starts, making it predictable, reliable, and easy to manage. Now, let's talk about a powerful feature in Docker called multi-stage builds. Multi-stage builds in Docker allow us to use multiple from statements in a single Docker file, creating intermediate images used only during the build process. This approach significantly reduces the final image size by excluding unnecessary build tools and dependencies, making our containers more efficient. Here's how it works. Imagine we're building a complex application. We need various tools and dependencies to compile the code, but these aren't needed to run the application. With multi-stage builds, we create a build environment with all the necessary tools, compile our code, and then copy only the compiled application into a smaller, cleaner runtime environment. Here's an example. In this Docker file, we have two stages. 1. Build stage, using the Golang 1.16 image, which contains all the necessary tools for building a Go application. We copy our code into this environment and compile it. 2. Runtime stage, switching to a minimal Alpine latest image, we copy the compiled application from the build stage using copy from equals builder. This results in a final image that includes only the compiled binary and none of the build tools. Benefits: smaller image size excludes unnecessary build dependencies, creating a smaller, more efficient image. This leads to faster downloads, reduced storage usage, and quicker deployments. Security: a smaller image with fewer components reduces the attack surface, enhancing security. Cleaner environment: the final runtime image contains only what's necessary to run the application, making it easier to manage and debug. In summary, multi-stage builds help us create cleaner, more efficient Docker images by separating the build and runtime environments. This ensures our final image contains only the essential components needed to run our application, leading to improved performance, security, and manageability. Thank you for watching our video on the structure of typical Docker files. We've explored various essential instructions like copy, run, CMD, entry point, and multi-stage builds. Understanding these components is crucial for creating efficient and reliable Docker images, as each instruction plays a key role in building, configuring, and running your applications. By mastering these Dockerfile instructions, you can optimize your development workflow, improve application performance, and ensure a consistent environment across different stages of development and production. We hope this detailed overview has provided you with valuable insights and practical knowledge to enhance your Docker skills. If you found this video helpful, please like, share, and subscribe to our channel. Don't forget to hit the notification bell so you never miss an update. Join us in our next video, where we'll continue to explore more advanced Docker concepts and best practices. Happy coding and debugging with K-Tips, and see you in the next one.